Alright, so in this video, I'm going to be explaining another important article with the title Neural Stochastic Block Model and Scalable Community-Based Graph Learning. This paper in 2020. So this paper proposes a novel scalable community-based neural framework for graph learning. The framework learns the graph topology through the task of community detection and link prediction by optimizing with our proposed joint SBM loss function, which results from a non-trivial adaptation of the likelihood function of the classic stochastic block model. Compared with the stochastic block model, our framework is flexible, naturally allows soft labels and digestion of complex node attributes. The main goal is efficient valuation of complex graph data. Therefore, our design carefully aims at accommodating large data and ensure there is a single forward path for efficient evaluation. For large graph, it remains an open problem of how to efficiently leverage its underlying structure for various graph learning tasks. Previously, it can be heavy work. With our community-based framework, this becomes less difficult and allows the task models to basically plug in and play and perform joint training. We currently look into two particular applications, the graph and alignment and the anomalous correlation detection, and discuss how to make use of our framework to tackle both problems. Graph community structure is an important research area. And in terms of graph topology, nodes in the same community tends to interconnect more often than nodes outside the community. So it can be viewed as a divide and conquer strategy. For performance, the hypothesis space for a large graph could be gigantic. For efficiency, no matter it is a social, a knowledge graph, or a biological network, the nodes outside a community intuitively tend to make less impact when a model learns a community. So the main contribution is that we develop a novel and general community-based neural graph learning that can learn from large-scale data and make efficient evaluation, and we show through extensive experiment that it helps improve performance for two applications. And this is the notation that K is the number of communities to detect. P is the stochastic block model. Z is the relaxed mixed membership matrix in our neural and our framework. And so they want to maximize this likelihood. If we maximize it, that we get this, because here they have the stochastic block model optimization, and it maximizes the objective, maximizes the likelihood. But we have several problems. If we just do this algorithm one, we have several problems. The first problem is it's non-differentiable, and optimizing it involves integer programming, thus it is not straightforward to integrate. Second, they also do not consider node attributes. Although there are recent developments like mixed membership, the probabilistic inference inevitably grows complicated with added parameters. Third, like many other probabilistic models, a trained SBM may still need inference that takes iterations to adequately evaluate new nodes. So soft assignment is a natural neural network with softmax layer. Also, it avoids expensive integer programming. Then we want to design a neural network such that Z is this. So we generalize the matrix C as the community similarity matrix. So we can see from this that thinking of C as similarity naturally allows edges being weighted or even associated with edge features. And so the general form of link prediction is this, and that's it. I mean, they talk about this entropy as well as a regularization. And then we add all of these things: entropy, SPM, stochastic block model loss, link prediction, labels, and then they combined it with neural graph embedders. That's the main idea. And did they experiment on YouTube? And so this is just a community-based large graph learning neural network with a loss function adapted from stochastic block model. Of course, it's not scalable.